Hello, welcome everybody to this EOL engineering seminar, and today we have Sunil Khatri talk to us, and actually Vivek is going to do the introduction since they are old friends and colleagues.
Thanks, Bill. Thanks for coming to the engineering seminar. Today, Professor Khatri will talk about two research and development projects very close to EOL, dropson, phaser radar. Sunil Khatri did this undergraduate from IIT Kanpur, Institute of Technology, in 1987. Then he did this master's in UT Austin, Texas. After that, he worked about 4 years in Motorola as a design engineer for electronics. It's very rare to have that kind of both academic, industrial experience. Following that, Motorola work, he went to UC Berkeley, did his work in, of course, CAD and electronics. Then he became a prof in CU. By then, I came to know him. He was a prof in CU. In fact, if you recall, Xilinx, it's a FPGA on the 119, close to Longmont. They have facility here. Used to teach a course. Then I asked Sunil, we have this microprocessor-based radar signal processor here. Could you make it to FPGA-based? The 2005, he was here for 3 months with his student. By then, some of radar people might know, Mitch Randall, he designed all the radar processors what we had here, PIRAC and YRAC, COTS. They're all become FPGA-based processors. One example of that one was when FPGA was used on the Eldora radar, which is airborne radar, where the weight came down more than 300 to 400 pounds because a new processor with an Arcane processor on the Eldora. So these are the things what he has done in 2005. Then I thought, well, we had a tough time with the phaser radar TR elements. I thought, well, is there a more than one way to design these TR elements? Monolithic circuits, that's where aerospace company do it. Could go differently. When I asked him, he said, yes, there's a possibility. Today, you would hear about this talk about chiplet, which is something different than a monolithic circuits. It's going to be attractive for building a prototype design, moving forward to even full-fledged scale. And so worked on two projects, I said, dropsons, and also TR elements, which is the heart of the phaser radar. I welcome Sunil Khatri to go for the talk. Thanks.
Thank you. Thank you so much. So I'm excited to be here. My name is Sunil Khatri, and I'm a professor at Texas A&M. And I've been here in NCOR for the last something like 7 or 8 months. It's been a great pleasure. So before I start my talk, I wanted to thank a few people for, first of all, Allison for making this happen and and enabling all this. So that was much appreciated. And then also on the two sort of case studies that I've done. One is the dropson. Got a lot of input and help and feedback and comments from Terry as well as from Mac. So thanks to Terry and Mac. And then on the transmit receive element, I wanted to appreciate Jonathan's work, then Vivek, as well as Eric Lowe. So lots of people to thank, lots of fun stuff that I've had in the last several months. I'll sort of describe how that all has gone. So what this talk is about is about chiplets and interposers. This is sort of a new way to design microelectronic systems. And the focus of the talk is more towards what do they mean for NCOR applications, right? Not really the other applications or researchy applications, but more like the NCOR applications. And in particular, the two applications that Vivek mentioned. One is a sonde, but it's like a golf ball sonde. It's sort of like the size of a golf ball. And the other is a TR element for a phased array radar. So let's see. Before we get into the NCOR stuff, I'll sort of do a brief sort of journey into microelectronics and sort of why in microelectronics, what is important, why sort of distances matter and such. So we'll do a little thought experiment, and following that, I'll talk a little bit about chip packaging, which is sort of central to all of this, to this discussion. And then we'll talk about this thing called chiplets and interposers, correct? And then say, why are we interested in chiplets and interposers? And then, of course, right after that, we'll say, like, what does it all mean for NCAR? What does it all mean for weather applications? In general, what does it mean for low to medium volume microelectronics applications, right? So the two case studies are the golf ball and the transmit-receive element, and then we'll talk about some future possibilities and where all this could go. So let's see, thought experiment. Suppose think about this, right? I got a printed circuit board 1 foot by 1 foot. This is something that we might have in a desktop computer or something, a foot long, 1 foot by 1 foot printed circuit board. And I have one chip chip A in the one corner of this board, another chip B at the other corner of the board. They have a wire between them, and they want to communicate. So the question is, what limits this communication? Where are the fundamental limits for two chips communicating on a board? This is basically key. This is sort of like the base thing that we need to understand when we're designing microelectronics systems. So what limits this? So first of all, we know the speed of light. 3 × 10⁸ meters per second, which is roughly 1 foot per nanosecond. When you think about it like that, it sort of sounds embarrassing. It's embarrassingly slow. Like in 1 nanosecond, this thing just travels 1 foot, right? It's sort of, it sounds weird to think about it like that. But now when there's electrons moving in on that wire that we just talked about between chip A and chip B, they actually slow down because they travel at the speed of light divided by the square root of kappa. Oops, sorry. Where kappa is the dielectric constant or the relative permittivity of the material on which the printed circuit board is designed. And that kappa typically tends to be 4-ish for printed circuit board material. Also for silicon dioxide on which we make our chips, it's also about 4, 3.9, whatever. So essentially, the velocity of wave propagation of the wire, of the signal from A to B, from chip A to chip B, is half the speed of light, okay? This means that if our signal launches from chip A and goes towards chip B, remember it was 1 foot, correct? So it's 2 nanoseconds for one side, 2 nanoseconds for the other side. It's going to take a time of flight of 4 nanoseconds to go from A to B, which in computer speak is embarrassingly slow. It's just 1/4 nanoseconds would be like the clock speed of if we were to generate a clock signal to orchestrate operations, which is a clock is the atomic operation that any chip performs. So our clock speed would be no faster than 4 nanoseconds, which means its clock rate would be just 250 megahertz. Now, just for context, right? My cell phone is way more than that, right? It's like a gigahertz plus, the speeds of of signals in the cell phone, or a motherboard of my desktop or something. So this is seriously limiting, correct? This 250 megahertz limit is a serious problem that we have. So many applications will simply not tolerate this. And so basically the motto of this whole exercise, this thought experiment, is distance matters for microelectronics. For microelectronics, I want to make things smaller. So the distances, if they are smaller, then my clock rate can be larger and I can have faster systems. So miniaturization in electronics historically for the last multiple decades, right, has basically been trying to make things smaller for this reason, right? So essentially, circuit designers have forever, striven to make circuits and boards smaller and smaller. By reducing distance, as we saw, we reduce the time of flight and our system can run faster, right? And also, one other trick we can do is, remember this velocity of wave propagation was speed of light divided by square root of kappa, so we can drop kappa, right? Hard to drop kappa too much and it's expensive, but we can kind of that's another knob we have to play with, okay? Now, all of this is sort of independent of what the chip is doing. So you can have digital chips or analog chips. It doesn't matter. It basically, regardless of the kind of chip, this thought experiment is applicable, right, in some sense. So whether the chip is digital, like a microprocessor, microcontroller, DSP, digital signal processing chip or whatever, or whether it's an analog chip, an amplifier, low noise amplifier, phase shifter, whatever, all of that basically doesn't matter. So I'll abstract away the kind of chip in the rest of this discussion, because a kind of chip doesn't matter. It's just the physical distances that we're going to focus on in some sense. Yes?
Just trying to make a very nice first slide. So what's the wavelengths for that? Is it about the same as the motherboard? An example you gave? It's for gigahertz, the wavelengths is
Comparable.
comparable.
Yeah.
So the signal propagation there is just one wavelength or so.
Yes, yeah, more or less. Yeah.
Thank you.
Okay, so now what are the key determinants of speed? So we're going to talk about some determinants of speed, which we'll sort of not discuss heavily in this slide, in this discussion, and some that we will. So let's start with, if I was a circuit designer, right, historically, what are the determinants of speed that I consider or what I think about? The first is electrical parasitics, and I won't focus much on this, this not being a heavy electrical talk, but there's resistive parasitics, resistance parasitics, and capacitance parasitics C, and the product of these is in the units of time, and that's a delay. So if I have a large R and a large C, my delay is high. So I want to keep the R and the C parasitics small. And when I say parasitics, I don't know if that's something that everybody understands, but parasitics are electrical sort of parameters that are parasites. They kind of slow us down. We don't like them, so we call them parasitics, right? But these are physically part of what, if I have a wire, I have parasitics, can't do away with them. So these are sort of things I don't like, and I'd like to minimize them. I can't make them zero. So there's R and C parasitics, which I want to keep low because their product is delay. And there's also, there's also inductive parasitics, L, and that results in a resonant frequency, which is 1 over square root L times C. And so again, I want to keep the L's under control. So these are sort of the parasitics that people consider. Again, I'm not going to focus too much on them in this talk. The two that we have talked about in our thought experiment are kappa. Of course, we would like to keep kappa small because C divided by root kappa is the velocity of wave propagation of our wire, right? Generally, it's hard to do that because smaller kappas are expensive. The best you could do is kappa equals 1, which is vacuum, which we can't do. Air would be close to 1, 1.1. But then I can't have wires floating around in air, for my electronic system, right? So essentially, 2-ish is a good lower bound for kappa practically in some sense. But the main thing that we can do as the first order simple-minded thing to do is minimizing distance. So we want to keep our distances in our board small, which will allow us to increase speed. So that's the best, easiest knob that I got, right? And so to do that, we want to use better, what are called packages, right? So I haven't introduced that. I'll introduce that in the next slide. So I want to use better and better packages in order to minimize this distance and maximize the speed of my system. So what is packaging and why do we need it and where, let's talk a little bit about history of packaging. Why do we need packaging and what is packaging, right? Packaging is something like this. See, there's a chip, which is silicon, where circuitry is implemented on this silicon. Now I can't, the silicon which implements my circuit, I'll call that a silicon die, okay? And that needs to be protected from the elements because if I leave it outside, there's water, there's all kinds of, and there's corrosion and stuff, and I want to protect it from that. So we cover it up with something called a package, okay? The other reason to have a package is that in the early days of of chip design, we had no way to connect these fine features on the chip on the die with a printed circuit board which had very coarse features, very large features. So we had to have something that bridged that gap. And that's where the package came in. So basically what a package does is protects the die and also allows me to interface it to a printed circuit board. And in the rest of this talk, my notation will be when I say die, I mean bare silicon with circuits on it without the package, right? And when I say a chip, I mean a packaged die, a die with the package on it. And also I might say chip or package die, which is basically the die with packaging. So let's look at what this package looks like, right? So here is an early package and a chip. You can see right in the middle here is a small little square looking thing, the shiny thing, I guess, right? That's the actual silicon. That's the actual thing that's doing the work. And all the rest of it, the black blob, is the package. So you can see how large the package is compared to the silicon. Now, I didn't need it to be that large. The only reason it was that large is because in the old days, we could not connect it to the board if it had the very fine feature sizes of the actual silicon. So we had to sort of spread it out. And plus, we had to protect the die from the elements and all that good stuff. But you can see the important thing here is that the silicon is extremely small compared to the package, which is an opportunity. If I could just directly connect the package to the printed circuit board, that would be a huge gain in terms of the size of the system. The system size would basically get dramatically smaller, right? So here are examples of early packages. They have various names, dual inline. They have 2 rows of pins, so we call them dual and inline. The pins are inline and all of this good stuff, right? So this is a dual inline package. The package on the right is called a flat pack package and so on. And these have large pins and long wires to connect the die to the pins, and so that causes high inductance, high inductance and resistance and so on. And that gives rise to a slower design. So these were early packages, and of course, if you looked at a cross section of the same packages, you can see the die right there, which is a really small thing. And then the package is this big blob around it. The die has very thin wires called bond wires that connect the terminals on the chip to the pins of the package and so on. And that's true for both the packages, the flat pack or the dual inline package. So now, of course, the next evolution, you can easily guess what people would have done, right? Like here we have pins on 2 sides of the chip. Well, let's go put pins on all 4 sides of the chip. Like that's the natural evolution. So that's kind of what happened next. We had pins on all 4 sides. These were the quad flat pack type packages. But once again, you notice the more important thing is, look at the die, the small die in the middle here, and the package. The package is way bigger than the die, and that's still an opportunity that we haven't, that gap that we haven't bridged, if you will. So once again, the package area is still much higher than the die area. So this is basically a continuing limitation. And future evolutions of packages had pin grids array. They have like multiple rows of pins that we had, But once again, you can look at the die, which is what's in the center here. The die area is much smaller than the package area. And this is, again, basically a big limitation, right? So this theme is continuing, is kind of what I'm trying to say. And the ultimate sort of, not quite ultimate, but the next evolution was where you had pins everywhere on the surface of the package. So this was what was called the ball grid array or the C4 packages. And again, here you can see the die area here. You can see the die on top. The die area is still smaller than the package area. The holy grail thing would be, what if the die area is equal to the package area? This is about as small as you can make the package, just the size of the die. And that's basically the bare die packages, which have been coming out more recently. And the bare die packages are where the die size and the package size are identical, excellent electrical characteristics, excellent parasitics, and opens up new frontiers for microelectronics. So this is basically the best solution. There's a small family of new packages that are coming out, like WLCSP. That stands for wafer level chip scale package. Basically, the die is the package, literally, right? And then you have these solder bumps on it, as you can see here. So that's basically what will allow you to connect this to the printed circuit board. So this is basically what we want, ideally, I guess, is the die and the package to be the same size. This will give us a small system, right? And so now I'm ready to talk about the interposer and chiplet sort of paradigm, right? But before I talk about that, I'll just talk about two competing paradigms that compete with the chiplet interposer paradigm. So where we've been so far, we just talked about how packages have gotten better and better to where the package is about the size of the chip, the die itself. That's the best it could be, right? Now let's talk about how these have been used in systems, right? So the competing paradigm for the chiplet interposer paradigm is the system in package paradigm. As the name suggests, the entire system is in the package. So you take this package, put it on a printed circuit board, really dense, and then that whole thing is the package. So in some sense, right, it's like a packaged PCB in a sense, right? So the whole system is now one package, if you will. Many of these microprocessor vendors will make processors like this, the Intels and the AMDs of the world. And these are high volume and they're medium to high volume. They're kind of expensive to build. So this is not something that's practical, but it is something that people will do, right? The other is a system on a chip or a SoC. Here the idea is, let's say I had a circuit board with lots of chips on it, and then the idea is let's just make a single chip that does all that functionality. And this is about as expensive as it gets because you're making brand new silicon that takes the functionality of all the chips that you had on the left side in the silicon and sticking it in one chip. So you're building new silicon. Again, super expensive, only viable for really high volume parts. So basically, high volume, high performance systems will do something like this. Classic examples are GPUs and processors and things like this, right? So the question becomes, is there something that I can have which spans the cost performance trade-off and has better, better end-to-end characteristics than the SIP or SoC? And that's where this chiplet interposer thing comes in. So in a chiplet interposer idea, this is more promising than SoC or SIP, great flexibility, and so let me show you why, right? In this chiplet interposer system, we have lots of degrees of freedom. So essentially what we have is you can see these little squares, these are chiplets. What's a chiplet, right? A chiplet is essentially is a chip, which is a piece of silicon that I can either fabricate myself, so I kind of go to a factory and say, hey, I go to a foundry and say, give me this chiplet with this functionality. Or I can get it off the shelf. I can just buy it from DigiKey, right? One of these chip vendors. So we can have, a chiplet can be a bare die, custom fabricated, from TSMC, right? The fabrication houses of the world. Or I can say, let me get it commercial off the shelf or COTS. I can get a COTS chiplet, or I can get a bare die COTS, or I can get a packaged die COTS. I have lots of flexibility in what I choose to be a chiplet, okay? So I get a bunch of these chiplets, and then I place them on an interposer, which is something that it could be passive. That means it's just like a printed circuit board material. There's no active chips in it, right? Or it could be active. It's silicon with actual logic in it also. So your printed circuit board could have logic in it in some sense, right? So this interposer can be some, passive with a low K, so it can give you the benefit of speed, as we just saw, right? And also distances are much smaller now because some of my chips can be bare die, so distances got smaller. I got a speed benefit from that. I got a smaller K, I got a speed benefit from that, so I can get a high-speed system doing this, basically. And then this interposer, at the bottom side of the interposer, has little C4 bumps or solder bumps, which allows it to connect to the printed circuit board. So that's essentially how it'll connect to the rest of my system. So essentially what I did is I have this great flexibility in choosing these chiplets. That's the key takeaway here. I can make my own chiplets, very expensive, or I can get them off the shelf, from commercial off the shelf from a vendor, right? And then it becomes cheaper, but it still retains all these benefits. So this here gives us a lot of flexibility. So you can have a very high performance system implemented in this method, which is the yellow font stuff. And you can have a low cost system implemented in this method, which is the blue font stuff. So let's go over that real quick. If I wanted crazy high performance, yes?
How are you defining a system?
A system is, let's say, a TR element's a system, for example. It's got all the chips of a TR element, or a Sonde is a system. It's got all the chips related to a Sonde, the GPS, the controller, the everything, right? It could be, if we do a non-NCAR example, it could be basically a microcontroller, microprocessor. It could be the motherboard for my phone or my desktop, the whole thing. Yeah. Okay, that's a good question. So a bare die is a chip without any package. So basically it's the raw silicon that implements the logic function that I'm implementing. So really quickly, I'll go back a slide or three. Let's see. Oops, I'm going the wrong way. Sorry. Yeah, no, not even this. So if you look at this one, this is an old style package. In the middle is the actual silicon that does all the logic, all the work of this chip. That's what I mean by the bare die. Everything else, the black, is the packaging. It's all the electronics, yes. And the packaging is just to kind of protect it and all of that. Okay, let's get back to where we were. So, yeah, so if I wanted a high performance system, what I would do is I would custom fabricate my chiplets, high cost, but it'll give me just the right chips that I want. And I will use a low K dielectric maybe, so I'll get an extra speed bump from that. And maybe I'll use an active interposer. So an active interposer, some of the logic can be stuck in the interposer as well. So this is what people will literally do for these high-end, LLM servers that they make for the GPUs and stuff today, right? They'll be the yellow kind of chiplets that they're making for these designs, for the the LLM servers for OpenAI and all of these things, the NVIDIAs of the world. And the blue stuff is the easy stuff to do, correct? Because I'm just using commercial off-the-shelf stuff, bare die or package die. I can buy that from the store, right? And I'm going to use a passive interposer. Again, that's cheap. So if I want to be on the low-cost side of things, I stay with the blue version of this slide, and I still get a performance benefit from PCBs. So I'm still winning, right? That's the cool thing about all this. Okay, now one little thing about chiplets, right? So the chiplets in the NVIDIA version that we just talked about, the LLM servers and stuff, they essentially will even use 3D silicon for some of the chips. Like the memories are actually stacked memories, so they're like 3D, there are multiple stacks of the same chip interconnected among each other. So that's what people will use. Again, that's not something I'm suggesting for NCAR applications or anything, but that's the high end of the performance spectrum. The other benefit of chiplets is that they can be heterogeneous. That is, I can use different kinds of chips that can't be manufactured in one die, but I can put them together on this chiplet interposer substrate, which is I can do emerging electronics. I can do optical stuff. I can do gallium arsenide, gallium nitride, silicon carbide, CMOS, flash. I can combine all these technologies all in one sort of substrate. So that's kind of the another of the touted benefits of the chiplet sort of paradigm. But now let's talk about the end. Let's say, how does this apply for NCOR? Let's talk about that. So for NCOR, right, fabricating chiplets, custom chiplets, that would be simply impractical and cost prohibitive because it's something that, the volumes are not large enough. So what I'm thinking is for NCOR applications, the best approach would be to use commercial off-the-shelf bare die whenever I can, so I can get the small size, can reduce the lengths of the sizes of the boards and such. Or if I can't get that, I can use commercial off-the-shelf packaged die, stuff I can buy from from vendors, right? And then on the interposer front, we would use passive interposers, organic or silicon. Again, those are on the less expensive side of things. This would still yield a very dense design, better than PCBs. And if you used an organic interposer that has a kappa of like 2.5, you already get a speed benefit from the kappa as well. So this is like a win-win for NCOR applications. So in some sense, it's like PCB on steroids, sort of. So with all this in mind, I said, let's do 2 case studies with NCOR. Case study 1 was with input and multiple meetings and feedback from Terry and Mac, was this golf ball sonde, right? We've been calling it a golf ball sonde. And the idea is to miniaturize the sonde design, and it'll have sensors for pressure, gyroscope, GPS, and a transmit back to the plane, correct? But the idea was to fit it into a golf ball. And as you'll see, the PCB is way smaller than a golf ball. Many of them will fit in a golf ball, I guess. And case study 2 was with input from Vivek, Eric, and Jonathan, right? And again, multiple meetings, discussions, and feedback. Is a TR element for a phased array radar. And this is basically one element of a LRU, or the line replacement unit, which has multiple of these TR elements. So essentially what we did is we take these 2 designs and just say, let's just take these designs and go through the whole chiplet interposer flow and see what comes up, see what happens, right? And essentially, let's get a feel for the gains that we might get. Now, the important thing is this is really early designs, right? So this is basically early study. Results are not complete, but basically they're close to what you would get, I think, if you actually build these systems. The general approach for the golf balls sonde, we started with a schematic of a sonde that I got from Terry. So then that was our starting point. We basically made modifications, discussed the modifications. Once we converged on the spec, we went through the whole flow. So the idea was all the parts that the sonde schematic that Terry sent, I tried to replace them with bare die, because that's when we get this thing to be as small as possible. So replace as much as possible with bare die, add a couple of sensors for the pressure and the gyroscope and whatnot, and then make a new schematic and then take it through the whole sonde flow, the whole chiplet interposer flow. With the TR unit, same idea. We started with a schematic of a TR element, which I got from Jonathan, and then replace parts as possible. Feedback from Vivek and Eric as to, hey, you can't change this part. This is too slow. This is whatever. Like some modifications to the initial schematic I made, and then back and forth until we converged on that, and then take the resulting design through the entire flow. Let's see what we got. And then we got what we got. So this is what I'm going to describe next, right? Sorry? Left? Okay, cool. Let's see. I think it'll speed up now. So the design flow has about 8 steps. I won't go through it in much detail, but there are 3 major steps. So one is initializing and placement. So we create the interposer. We kind of define the interposer size, the structure, the layers in it, and all the technology settings for the material of the interposer. So that's sort of the first step. So that's kind of like just the interposer part of the picture you see on the bottom left. Then we come up with the dies that we get from the data sheet, and then the data sheet die has pins, so we mimic the locations of these pins in a text file, and then load these die. And then in the third step, we place them. So you can see this in the last picture on the right, there's this interposer, which is this black structure, and it has 6 dies placed on it, correct? You can see how densely they're placed. So these dies are now located on the interposer substrate. The next steps, we're going to route them, okay? So we'll define what signals get connected to what, create the I/O pads and sort of define the connections that we need to make, and then define also the power supply and ground signals and where they are and what the power supply and ground buses are. And then finally create the C4 bumps, the bumps that connect the interposer to the printed circuit board and proceed from there. Finally, we place and route the whole mess, and that's a final design we get, right? So let's see what all happened with this flow in the golf ball sonde, correct? With the golf ball sonde, this was a schematic that I got from Terry to start with. These are the parts that we replaced. So on the left of this table, you see the parts in the original design. And then on the right are some parts we replaced them by, which are equi-performance parts, right? And we also added more sensors like the pressure sensor, the accelerometer, and the power switch and stuff. So this was basically all the parts in our version of the new design. And you can see,
Where is the humidity sensor?
I'm sorry, there's no humidity sensor in the golf ball. So that's hard to do because it needs ventilation and stuff. But that's a great question. So this is no humidity sensor, just a pressure sensor and gyro. So this is our schematic that we used to go through the flow. And then once I kind of skipped all these steps, but when we get to about the last step of the flow, this is what the interposer looks like. It's about 10 millimeter by 9 millimeters, so about a centimeter by a centimeter, roughly, right? Super, super, super small. And then this is finally after placement and routing. This is a 3D perspective view of the placed and routed golf ball sonde interposer, right? And I'm going to zoom into spots of it. This is a zoom in of the controller chip. And you can see these bumps, which are the C4 bumps that connect to the printed circuit board. And there's some extra ones. We don't need them all, right? And you can also see, those are called C4 bumps. But you can also see on the front side of the interposer, you see these micro bumps, which are the ones that connect to the chips. So there's micro bumps on one side of the interposer connecting to the chip. The bottom side are C4 bumps, which connect to the rest of the board. Another cartoon of the power supply grid on the interposer, again, a perspective view. Some more zoom in on the power supply. You can see the C4 bumps and also the micro bumps and stuff. And then these are some signal connections that are routed. So these are, you can see 4 or 5 chips here, and there's some signal on these different these chips are getting connected to other signals and stuff as well. Let's see. So then we said, let's look at the thermal characteristics of this, right? Like when it's operating, how hot does it get and all that good stuff. So essentially on the left, we got from the data sheets the power consumption of each of the parts when they are operating. And then we basically did a thermal simulation of the interposer with these parts on it, assuming that they're consuming the power that you have on the left side. We assume a heat sink, which has a heat transfer coefficient of 350 watts per meter square Kelvin. This is assuming basically Newton's law of cooling here. And then, simulating this, we see that the temperature range of everywhere on the interposer is just between 30 and like 38 degrees centigrade. So it's not like burning up, right? Then the cost. So we take these chips, and if we bought them in lots of 100, then these would be the cost of individual chips. the total cost of just the parts would be $145. Now, the interposer costs about $15K for 1,200 centimeters square of interposer material. So that would yield about 1,200 interposers for us because we have 1 centimeter square for our interposer. So that means around $12.50 for the interposer, assuming you're doing, you're building all these. So the total cost is just like $150 for the whole mess, right? Like, and the cost is dominated by the parts. It's not dominated by the interposer fab. So then same kind of exercise with the transmit receive unit. So we'll kind of look at this as a schematic I got.
Loaded, $1,000. 1,000 for each sample.
But it has humidity as well, so this thing does.
Yeah.
So the schematic diagram of that transmit receive unit here, which I got from Jonathan, and this table describes the original parts and how I replaced them. You can see I basically wasn't able to replace many parts. I only replaced 4 of the 10 parts here. The others I used as they were in the schematic. This here now is the last but one step of all the components on an interposer. This interposer is 2 centimeters by 1 centimeter. It's kind of tiny, right, for a TR element. And then after routing, power, round, and signal, this is what it looked like. This is a 3D perspective view of the routed interposer for the TR element. And then, of course, the interesting thing here, which Eric was worried about, is what about the temperature profiles of this? Because this is a power-consuming beast, right? So again, on the left is the power consumption of all the different components, which is an 8% duty cycle for transmit. So this has every one of the components and their power consumption. Assuming, again, a heat transfer coefficient of 350 watts per meter square Kelvin, which is a good heat sink, okay? With a good heat sink, my temperature profile is something between 40 to 85 degrees. Not so bad, right? But if I put my finger on that, it'll probably burn, right? So then, you could use better heat sinks. But also now you can go nuts and say, let's go use liquid cooling. Suppose you did a liquid cooled system, then the temperature profile would be from 25 to like 37 degrees centigrade. So these are sort of the extremes. If we looked at the cost, component costs are something like $290. Again, from the previous calculation, the fab cost would be about $15,000, which would end up being about $25 per interposer. So the total cost would be like $315 per TR element, of which $290 is components, is electronic components, and the $25 is the interposer. So let me sort of close with some conclusions, right? I think if this paradigm is useful for NCAR applications, in my opinion, the idea would be to use commercial parts, not fabricate integrated circuits, because that's cost prohibitive. Commercial parts would give the speed and density which are which are better than what printed circuit boards could do. So that's kind of a perfect match in some sense for NCAR applications, in my opinion. I think the 2 case studies support this conclusion. What still needs to be done is I got to extract resistive, inductive, and capacitive parasitics from the interposer designs we have, and then run a circuit level simulation to see that all the circuit level parameters are working correctly, or the circuit performance is matching, and all that good stuff. So that's one thing that has to be done. Also, it would be fun and useful to just take one design from beginning to end, and fabricate and quantify and just see the pros and cons of this design with respect to existing designs, and see and this would be a lot of learning from something like this. Now the other thing is, look, with the current designs, I started with a schematic which I got from Jonathan or or Terry, and I just pretty much monkey see, monkey do, copied that schematic in some sense with slight changes in the parts that I got. But if I started from a high-level specification instead, then maybe we would use a completely different design, and that might give us some extra benefits, might become smaller, and might become more, a better design. If we started from scratch, this was nowhere near starting from scratch. It was just trying to mimic an existing schematic here. And then I need to get a little more precise fabrication pricing. I'm going to have a Zoom call with the fab vendor tomorrow, and then I'll get a better idea of where the costs are and such. So finally, the caveat is that current case studies shouldn't be considered complete. They're kind of like initial sort of starting sort of, kicking the tire kind of experiments, and hopefully they should be reasonably accurate, but things will change a little bit if we were to build this. That's the end of my talk.
Thank you very much. That was awesome. Great talk. So there are people online, and so if you have a question, please wave at me and I'll hand the microphone. And if you are online, please use the Slido system, which should be showing up on your webpage somewhere to ask the online questions. So if you would like to kick it off. Terry.
I've got the
How many questions do I get?
Sorry?
I've got the ceiling mics on. You don't need to do that.
Oh, great.
You don't need the mic.
Don't need the mic. Okay.
Okay, great.
Just speak loud.
So thank you. It's fun to see this, I'm going to say new technology. Where is the maturity level in the commercial world as far as actually manufacturing this? Because to me, this is certainly a new approach to packaging electronic devices. And who's the big user right now of this type of technology?
Yeah, so
Because I look at it, the advantages could be shrinking, speed, but and I'm not sure if we're quite there for those needs here at NCAR, but it certainly looks like the future.
yeah, so there's this vast space of like performance to cost, right? So on the high performance side, all these servers for ChatGPT and Anthropic and so on, the NVIDIA servers, they're using the high performance side of these things with very aggressive 3D structures for memories and GPUs and stuff. So they're using the extreme end of this, the high performance end. I think that most people haven't realized that there's on the low cost end, there's massive opportunities to replace PCBs. See, that's not something that's being actively pursued. And that's why I think this is an opportunity, because people just do PCBs, and then this is something that's like not very front and center when they're designing systems like this. That's where the opportunity is. That's where the opportunity for products is also, and also from a learning point of view and a sort of a research point of view in some sense. There's also bleeding edge research side, which is something that I plan to do, but this would be not very relevant to what we're doing here, right? Which would be to use active interposer research. I have some ideas on clocking and so on. So that end of it is super high end and extremely expensive because they fabricate custom chips for it and so on. But on the low cost side of things, right, there's tremendous opportunities. Vendor-wise, there's some university in the U.S. There's some university vendors that will fab, like passive interposers. That's the ones that I've found. There's a group at ASU that does this. There's also a group at Purdue that I'm going to talk to, and let's see what they're doing. I did talk to some commercial vendors, and for them, I think the volumes are not enough to be of great interest and such. So. But a lot of the vendors for fabrication of interposers are overseas. So I don't know if that answers the question, Terry, but yeah.
Awesome.
Okay.
So we have an online question from David. Is there a process for adding the passives, decoupling capacitors and resistors to the interposer boards, i.e. doping sections?
I like it. Yeah, so I love that question. So I think the question says, can I dope portions of the interposer to make resistors or to make capacitors or something? The short answer is no, but this could be a fun thing to try. But again, the interlayer spacings on the interposer are far enough that you wouldn't get good capacitors, for example, if you wanted to do that. So I think that there's no process natively from the interposer vendors I'm talking about to do something like this. If I wanted to do it anyway, I wouldn't get a high enough capacitance density to warrant doing this, I guess.
Sorry if I missed it, but physically, how are the interconnections on the interposer made? And that's the fabrication house that makes the interposer, or that's
Yes.
the stuffer that does that?
Yeah, so good question. Let's go look at this. So this is the interposer. The idea is what I would do. I'd go through the flow, and my last step would be the routing, and I'd get these design files. It's like Gerber files you send to a PCB vendor, right? I'll get these design files that I'll ship to the interposer manufacturers. Like, here are the files which would specify the size, the interconnect, and all of that. They would fab that, and now I can optionally have them send me back the interposer, and I buy my own parts and connect them, and like solder them and stuff. Or alternately, I could send all the parts to the same manufacturer. They would assemble and return it soldered on, both of those. And I'm, because the feature sizes are small, the vendor I'm talking to, I'm saying, you do the manufacturing, you do the assembly, just send me an assembled board. With, I'll send you the design files, I'll send you all my components, solder them and send them back to me. That's the idea. The number of layers you have on this, the way we've done it, you can have up to 5. We've done 3. 3 is so more than what we need. I mean, 3 is just right. I wouldn't need 4 or 5 unless you have a very wiring dense design. But you can easily go up to 5. The vendor I'm talking to from ASU, they can do 5. 5 layers. It's kind of like a 5-layer PCB, sort of. Yes.
What are the typical assembly costs for, say, the golf drops on 1 centimeter by 1 centimeter?
Yeah, so the assembly cost, right? Everything would be included in this 15K that we're talking about. This 15K breaks down as, the cost of the interposer, the cost of 1 layer, and then, minimum 3 layers. If you want 2 more layers, it's $700 more. I mean, when I added it all up, it's about $15,000. And a caveat is there's a Zoom call I'm going to make with them tomorrow. That number will be refined when I do that. But
There's a online question from Adam. We threw out the 15K number a few times. Is that roughly the minimum order quantity?
correct, Adam. So hi, Adam, by the way. So 15K, yes, is for this is for a silicon interposer. There are 4, you have to buy 4 wafers at a minimum. The sum total of area that you get in terms of the interposer area for 4 wafers is 1,200 centimeters squared, which is what I've been writing in those slides. So 15K for 4 wafers, which actually is 1,200 centimeters squared of interposer surface. Does that make sense? How mature are the design simulation tools? And hi, Eric, again. These are quite mature, Eric. Of course, we had, learning curve problems, like, okay, something sometimes won't work, and then we had to contact, somebody at Cadence. By the way, the company that makes these is called Cadence Design Systems. Same company that makes CAD tools for chip designs, but now they've sort of expanded it to interposer and chiplet designs as well. So their tools are quite solid. Like, for example, the simulation, let's see. The tools that I would use for SPICE simulation, this extremely mature. The place and route, I mean, if you look at this entire flow, individual steps of this, theoretically, the tools that we do for them for a real chip design, very mature technology, and they've been adapted to the chiplet flow. So I think that, once we got going, we didn't have much trouble, so I suspect that the tools are pretty mature.
Sebastian.
And of course, sorry, And of course, as we do this, right, we'll find bugs and we'll have bug reports to send to Cadence, I'm sure. But they're generally quite good.
Yeah, you mentioned that you could have the manufacturer of the interposer place your chiplets on it. If you chose to do that, what would be the added cost, or how difficult would it be? Like, what kind of infrastructure would we need to be able to
do that.
To do that here in the house?
So, another good question. So if I let me get to that slide. So this 15,000 that I mentioned, it includes assembly, right? If I said I'll save a little bit and do the assembly on my own, I'd lose my eyesight before I'm done. Because these features are extremely small. And for example, right, like some of this, if I have bare die with solder ball connections on my chips, let me see, sorry, I'm flying through too fast, but sorry about that. If I had packages, oh, come on, it's going too far back. If I had this kind of package, correct? Sorry, with the solder bumps on the bare die, the solder bumps have to touch the surface and I have to melt it just right. I have to heat it just right for it to fuse with the printed circuit board. So that's something in-house in my lab at A&M I simply couldn't do, because if I overdo it, they'll all short. If I underdo it, they don't get a good connection. So this type of stuff I'll just stay away from, and so I couldn't do it. I couldn't see below the chip to see if I'm making the connection properly or not. So this is best done with, with someone who has the right equipment.
Chris.
So there was mention with the golf balls of there's no humidity sensor. I assume it's very easy to integrate something like a low frequency sensor that just has wires and
I would defer to Terry on that, but when we started this, so when we started this, I found a pressure, temperature, humidity, sensor, and I was all excited, and I showed it to Terry, and he said, "This one's no good," because it's just a very large time constant. I think Terry, is that what he said?
It's meant for measuring here things at the surface, not up in the atmosphere.
So really bad for atmosphere. But if there's a good sensor that we find someone makes, we could put it in there.
So, go ahead, Walter.
Oh, well, okay.
Yeah, I have a question. I mean, the chip market, is very mature. You find all parts in chips, but can you find equivalent parts just as bare dies? How makes sense does that market?
That's a fabulous question. So many of them you can't. But okay, so you remember in this exercise, I had a schematic I started with. Sorry, I had some schematic I start with, and I say, now let me find bare die for. Sorry, I'm just flying too many. So I have some schematic, and I'm saying, let me find bare die for equivalent parts in the schematic, but I'm not changing the schematic. That makes it hard because I might not find bare die. In many cases, I used package die for that. But in the golf ball son, you can see I have bare die here, bare die there. I got two with bare die, and I was like, woohoo, I got two chips that I'm using as bare die. If I was to start from scratch from a spec, then the opportunity space of looking around for chips is higher, and I can find maybe more bare die. But there is an ecosystem now where more and more die are being sold as bare die from DigiKey even, right? It's like, so this is getting to be, the ecosystem of bare die is growing, which is kind of the right direction for something like this.
So we pretty much used up the hour. Vivek, maybe can yours be the last question, please?
Yeah, I have just a comment. When I started the project with Professor Khatri, always I thought elephant in the room was TR element. No, phaser radar is so expensive. Can we make it? Even Serafin asked me, what are you working on? Can you make it localized? And compared with what we can do with the C-band APAR radar, just on what I know in the industry with working with other engineers, my thinking is, given that if we could do it right, we can reduce the price of a C-band phaser radar or 2 meter size, what you propose, by factor of 2 or 3. Could be done. but this is something you can explore and look at it in the future. That's my comment.
Thank you. So I think, Sunil, you are here for one...
Till the end of the month.
until the end of the month over in FL1. So I'm sure he had welcome visitors to drop by and talk more about these questions.
And
but
my email
email
address.
is, oh, there we go. There's his email. So let's thank him again very much, and thank you everybody for coming.